Welcome to ECE 302. This is lecture 5.1 on joint PDF and CDF. I'm Professor Stanley Chen. In this chapter, we are going to learn about a very new idea, which is the subject on joint random variables. You may ask, why do we want to study joint random variables? The reason is very simple. In many practical engineering problems, you're not just seeing one random variable. Oftentimes, you're seeing two or more random variables that are interacting with each other. The subject on joint random variable is about dealing with the interactions between random variables. In some problems, we know one random variable and we want to see how will the other random variable be affected. You may have heard the term correlation between two random variables. How would one influence the other? You may also see problems, for example, I have a conditional distribution, then I have one random variable, I know what it is, and then I would want to see what will happen to the other random variable. So the conditioning becomes a very important topic. In this chapter, we're going to learn about all of these. As you can see, it will be an extension of what we have learned in chapter 3 and 4 on discrete and continuous random variables. So to start with, I want to define joint distributions. Joint distributions really means high-dimensional PDF, CDF, or PMF. In the previous two chapters, when we talk about random variables, we are usually focusing on a single variable. That means you have a one-dimensional function, that is the PDF or the CDF. It is a one random variable, and so you have only one x here. It is a 1D function, so you have one input over here. That is a 1D PDF or CDF. This idea can be very easily generalized to two random variables. For example, you can have a pair of random variables, x1 and x2, and without any complicated definition, I can just say that I will want to extend this one-dimensional variable to two-dimensional variables. So you have x1 and x2. This is defining a two-dimensional function, and this function is what we call the joint distribution. And of course, if you want to have three random variables, you can put them into this form, and eventually you can have n random variables altogether. So you may wonder, how would it ever be possible that I need to encounter more than one random variable? And in fact, encountering two or more random variables is very often. Let's say you're looking at a coordinate in a space. So let's say this is your space, and then you're finding a coordinate. This coordinate is given by x1 and x2. Okay, and you say, what is the probability that my coordinate is appearing inside this region? This is already a two-dimensional problem where you're finding a coordinate in a 2D space, and you find the probability of getting that coordinate. And so you're asking, what is the probability density function of this pair of coordinates? Okay, x1 and x2, they are the two numbers of your coordinate. What is the probability of getting that? That will define the PDF. Now you can extend this idea to a three-dimensional space, and then you have a volume in a three-dimensional space, and then you're looking at one coordinate over there. That would be a three-dimensional PDF. In general, you can have n random variables. You can have an n-dimensional space, which is very common in the data analysis we do today. So in general, what we can do is that we can say that I have a vector of random variables. This is denoted by a bold capital letter X with a small letter X that denotes the state. And these states, you have these variables x1 through xn, and then you have these capital X that denotes the random variables. So this chapter, chapter 5, is all about joint distributions. They are the high-dimensional PDF, PMF, or the CDFs. Why do we want to study joint distributions? Let me give you one particular example to motivate the discussion. In image analysis, people have been developing a lot of data sets. One of the well-known data sets is called the ImageNet dataset that was published back in 2010. And this dataset has changed the entire landscape of deep learning, because before then, we only have very small data sets to train deep neural networks. And since the invention of this ImageNet dataset, we are now able to train a very, very complicated deep neural nets because now we have enough data. Have you ever wondered what are the distributions of the images? Why are they so meaningful to train deep neural networks? If you think about deeper about an image is basically a collection of pixels. These pixels, they are numbers. So I can all represent an image. For example, an image here, I can represent it as a very, very long vector. The vector contains different colors, different intensity values, but they're basically numbers. Okay, it is an extremely high-dimensional vector. For example, if you look at the ImageNet dataset, each image will be 228 by 228 by 3. That is a huge number of elements, but nevertheless, they are vectors. I can represent it as a vector. And then I have a lot of these images. All right. So if each image is a vector, and a vector can be represented as a coordinate in the high-dimensional space, then all these images, they will form a manifold. This manifold will define the shape of the distribution. So here I've just called it an fx, and this of course is a cartoon illustration of what's going on. And you have a vector that is a particular image. This particular image will fall onto one point in this high-dimensional manifold. And the meaning of that level or this color coding means that the probability of getting an image. For example, if the data set contains dogs, and suddenly you have an image of orange, then of course the orange example will be unlikely to happen in your dog data set. Vice versa, if you're looking at a dog data set and you have a specific breed of dog, for example, golden retriever, then you will say that there's a high probability that this image will show up because all these pixels, they may have some yellowish pixel values because this is a part of a dog, versus it's unlikely to get an orange. It's completely orange in color. So you can imagine that this high-dimensional distribution really tells you something about the distribution or the likelihood of getting an image out of the entire data set. So knowing this distribution or this high-dimensional representation of the image, that actually helps us to understand a lot more about the underlying working principle of many classification algorithms. So this chapter, of course, we're not able to deal with big problems like ImageNet or training deep neural network. However, knowing that all your images can be represented as vectors, and then the distribution themselves can be represented as high-dimensional PDFs, that single message alone will be very, very enough to motivate the discussion of learning what are the meanings of joint distributions. Why do we want to study 2D PDF, 3D PDF, or n-dimensional PDF? I hope that has motivated you to do so. Here is the outline of this chapter, and in particular of today's lecture. We're in the beginning of this chapter 5. We want to talk about joint PDF, CDFs. Later on, we will talk about expectations, conditional distributions, and so on. For today's lecture, I want to focus on the basic principles of joint PDF, CDF, PMF, and all sorts of things that are around that topic. Okay, so by the end of today's lecture, you'll be able to expand your tool set from single, continuous, or discrete random variables to a pair of random variables. It's very simple, just 2 random variables, and you will see that a lot of these concepts are transferable from the 1D case to the 2D case. The only difference will be that we are now integrating a 2-dimensional space, instead of integrating in a one-dimensional space. That's the biggest difference. All right, so without further ado, let me start by talking about the content. Let me start by talking about the joint PMF, which is a very easy concept. The joint PMF is, of course, defined for discrete random variables. It is defined as a two-dimensional probability that involves x and y. X is the random variable for the first coordinate, y is the random variable for the second coordinate. The joint PMF, of course, it will be a function of two random variables, and you can see that this is the joint PMF notation. You can compare it with the PMF of a single variable. In chapter 3, when we talk about a single variable, we write a p of x, and then there is an argument of small x. This is a 1D function. Now you have a pair of random variables, x and y, and so you have these two arguments, small x and small y. Now, what is the meaning of this pxy of xy? Now, we can go back and ask what is the meaning of this PMF. This is really the probability that x equals to x, because it is a discrete random variable. When you have a pair of random variables, you can extend the idea to have x equals to x and y equals to y. So basically, you're asking the intersection between two events, x equals to x and y equals to y. Pictorially, it is quite easy to understand. So instead of drawing one-dimensional function and then you're looking at the impulse, you're drawing an area in a two-dimensional space. And then you're looking at one delta function, and you ask, what is the probability of getting that? Now, of course, it is a discrete space, and so you can count each one by one, and then you go to here, and then you ask, what is the probability? The probability would be x equals to this particular value, this is my small x, and y equals to that value, that is my small y. I'm looking at this coordinate only. Okay, now if you go back to this diagram here, here is your y, here's your x, and then you're looking at this point. This point has a probability of pxy of small xy. That is the definition of a joint PMF. And let's look at an example just to make sure that you understand what it means. Suppose we have a coin, and then we want to flip the coin, and then we have a dice, we call it y, the coin is x, and then we want to find the joint PMF. So imagine that this is a fair coin, it's a fair dice, then the sample space of x will just be 0 and 1, the sample space of y will be 1 through 6. That's trivial, right? Okay, now how about the joint PMF? The joint PMF can be written in terms of this table. This table has how many elements? You have 2 elements for x, 6 elements for y, so altogether you have 12 elements. These 12 elements, because I'm not putting any assumptions onto the values, I will just say that they're all equal. And therefore, in this table, all these 12 elements, they have equal probability, so they have 1 over 12. Now, what is the PMF, the joint PMF? Well, the joint PMF will just be P of xy at small xy, and that equals to 1 over 12. Like what? Like I can ask, what is the probability of xy? X will be 1 and y will be 4. Okay, so x equals to 1 and y equals to 4, so it will be this number, so that would be 1 over 12. See that? So this is a very, very simple extension to the one-dimensional PMF. In the one-dimensional PMF, you don't need to worry about the values of the other variable. For example, if you're only looking at y, you just look at one row of this thing. You don't need to worry about the x. Okay, so for the 2D case, you need to look at both x and y, but that extension should be pretty straightforward. Now let's look at another example. Suppose in using the same example, you have a coin, you have a dice, and then you want to get the probability. And let's define 2 events. A is that x plus y equals to 3, and then B is that the minimum equals to 1. Okay, so let's look at the probability of A and B separately. So the probability of A is what? Well, according to the definition, you just need to go to the space, okay, This is your area, and then you count the number of pulses that are living in the area that you are looking at. For example, you're looking at this event A, you just count all the pulses inside this event set A. So therefore, you're taking a summation of all the coordinates inside A, and you sum everyone out. Now, how are you going to get x plus y equals to 3? So let's go back to this table. X plus y equals to 3 can happen when you have x equals to 0 and y equals to 3. That will give you 3. Okay, and then how about another case? So x plus y equals to 3. What else can you get to 3? How about this number? X is 1 and y is 2. That will also give you the sum equals to 3. And therefore, you can write down all the possible cases. It would be 0, 3, and 1, 2. You add them up. This is 1 over 12. This is 1 over 12. You add up, you get 2 over 12. Is there other possibilities? No, because if x is 0, y is 5, then the sum will give you 5. X is 1, y equals to 1, the sum will give you 2. So that will never give you a 3. Okay, and therefore the probability of this event A can be really written as the sum of these two impulses. Each of them is 1 over 12, and so you add up, you have 2 over 12. The event B can be calculated in a similar way, where now you look at this minimum of xy equals to 1. So this is a little bit more difficult problem, but it's actually not too bad. Let's take a look. You want the minimum of x and y to be what? You want the minimum of x and y to be 1. Okay, so you go to this table again. If your x is 0, y is 1, what is the minimum? The minimum is 0, so that doesn't count. Okay, your x is 1, y is 1. The minimum of 1 and 1 is 1, so this works. How about here? The x is 0, y is 2. What is the minimum between the two numbers? The smaller value, that is 0. So that doesn't work. Here, does it work? 1 and 2. 1 and 2 will work. Okay, so we continue. Actually, for all the zeros, they don't work because the smaller will always be 0. That's not 1, right? Because we're looking at the minimum equals to 1. How about this row? This row says that anything that is less than 1, that will work. So all these numbers will work. All right, and therefore, this event set B will contain all the coordinates that contains 1 through 6 for the y, and 1 has to go to the x. And so you sum all these numbers up, you have this 6 over 12. That is your probability of getting B. Okay, so I hope this example, these two examples, has illustrated the difference between a 1D problem and a 2D problem. In fact, there isn't too much difference. The only difference is that previously you need to calculate in the 1D space, and now you need to calculate in 2D space. Previously, you just count the number of impulses, and now you're still counting the number of impulses, but in a 2D space. Okay, so in fact, doing this kind of calculation, in principle, is not that hard. Going from 1D to 2D, as long as you're familiar with the calculation, the definition in 1D, the calculation in 2D is quite easy. Now let's talk about the continuous case. Suppose you want to define a PDF instead of PMF. Now recall that in the 1D case, the probability of a continuous event is just integrating over the event set A, and then you have fx of small x, and then your dx. That will give you the probability of the event A. All right. So now you ask, how do I extend this idea to two-dimensional space or even higher dimensional space? Then just look at this PDF. Replace this 1D PDF by the 2D PDF. Instead of integrating dx, you integrate dx and dy. Period. That's all about this joint PDF. Is the extension from one-dimensional PDF to two-dimensional PDF. Now, what does it mean pictorially? Pictorially, instead of just integrating the function over a range of values, you go to a space and you crop out a service. You look at the area inside the service. And this area has to be a square or rectangle, depends on what is your dx and dy. And you go to this area, you integrate using this function fxy. That would be the probability. So here it would be the idea. This is the event set A. This is your event. And then here is your probability values. And then you go to this event, you count all the numbers, and then you integrate them. That is summing over this entire curved surface. You sum all the numbers up. That will give you the probability of the event A. So let's look at an example. Suppose you have a uniform joint PDF, which is defined in a 0, 2 square. So what it means is that you have a sample space. This is from 0 to 2, 0 to 2. And then you can draw the PDF. The PDF is a joint PDF, and it is uniform, so it will have a flat surface. Okay, and then this flat surface, you want the height to be what? Well, since it is a PDF, of course you want this PDF integrating of pxy, of small xy, dx dy over entire 0, 2, 0, 2. You want it to be a 1, because that's just integrating the entire sample space. You want it to be 1. And now you ask, what is that number? That number, since this is uniform, it is just a constant c. So you know that this is 4c equals to 1, right? Because you integrate this constant c, you integrate x from 0 to 2 and y from 0 to 2. That's eventually just calculating the area under the curve, okay? So that will give you an area of 4. And so you calculate the c, so c equals to 1 over 4. So that would be the height. The height would be 1 over 4. Okay, so now you have this 1 over 4 here. Then you know that this is your PDF. And then now you define a event. A is between A and B, cross with C and D. So essentially what you have is that you have this area here. This is A, this is B, this is C, this is D. So if A, B, C, D, that is the area. And so you ask, what is the probability of getting this A? Well, the probability of getting this A is the probability that X is between A and B. And, so this comma means that it is an and. This is Y is between C and D. So you integrate this thing. So you integrate dx from A to B, dy from C to D, and then you have 1 over 4 here. And then you do this two-dimensional integration. That shouldn't be too hard. So you have D minus C times B minus A divided by 4. That is exactly the area given by this function. Okay, so I hope this example also shown you that the calculation of a two-dimensional PDF or the probability is not that hard. Just plug in whatever you're given about the distribution, put into this double integration, and then solve the double integration. You'll be able to find the probability. Let's try another example where you have this B is equals to x plus y less than 2. So let's draw the diagram here again. So I want to make some changes here. Here I'm drawing a little bit complicated. It's a three-dimensional surface. But indeed, if you can follow me, I think you can see that I can just project everything back to a 2D space by saying that this is x, by this is y, right? These are just the same thing. I'm just saying that I want to put an eye over here, and then I'm looking down to see what is going on in this distribution. So this is the top-down view of the distribution. So originally you have this 0, 2, 0, 2. This is your sample space, and then you're looking at A and B. So this is A, B, and then this is C, D. And so we have found this probability in the previous example. Now let's try another new example here. In this example, I'm going to define an event B. This event B is defined as x plus y, and then this is less than or equals to 2. Okay, so what is that? Now, first of all, we need to understand the meaning of this set x plus y less than 2. So if this is the coordinate of y, this is the coordinate of x, this has to be a line. Okay, so let's just look at this line, x plus y equals to 2. This has to be a line, okay, a straight line. Now, what's that straight line? This is equivalent to saying that y equals to minus x plus 2. Do you guys follow me? Okay, so this, you move this x to the other side of this equation. You have y equals to minus x plus 2. And then you look at this equation. This is the slope. Slope has minus 1. The y-intercept would be 2. Okay, so what is the curve? The curve has to be a straight line. This is your straight line. The straight line has to be like this. Now why? Okay, so slope has to be minus 1, and so this is correct. Now when x is 0 and the y would be 2, that is your y-intercept. So that is the 2. Okay, so this is the straight line representing this equation. And then you ask, what is the region? Is this region, because this is a set, this is a set that defines all the x plus y less than equals to 2. We ask, okay, among this all these this is your sample space, which is a square. Are we looking at this half or that half? Okay, now one very simple way to do this problem is that you keep the inequality sign here, and you keep the inequality sign here, and then you plug in a number. Okay, for example, plug in this number and ask 0, 0. Okay, so is 0 less than minus 0 plus 2? Is this correct? If it is correct, then that means this inequality is true. If this is not correct, then this inequality is not true, right? So now I plug in the 0 and 0, and I check that this is actually true. And therefore 0, 0, this origin, this coordinate, has to be included in your set. And so would it be on the upper half or the lower half? Clearly it has to be in the lower half. Okay, so now you look at this diagram, you see that, okay, what is this event B? This event B is written by this equation, a little bit complicated, but nevertheless, it's just a lower triangle of this diagram. So what is the area of this lower triangle of the diagram? This lower area, if I know that there's a square, so the square has area of 1, then this lower triangle, of course, has an area of 1/2. Okay, without doing any calculation, by looking at the diagram, I know that it has to be 1/2. But I know that many of you want to look at the equations. So let me just walk through the equations with you to make sure that you understand this idea, because this will come back over and over for our problem. So what is the PDF? The PDF, of course, is your 1/4. This is your PDF. And then let us look at this integration. The integration, I need to integrate dx and dy. But I'm not integrating from 0 to 2 and 0 to 2. If I put on 0 to 2 for both, I will be getting the entire square, which is not what I want. So what do I want? Well, let's look at this dx. The dx has to be integrating from 0 all the way to where? All the way when you hit the blue line. And this blue line is given by this equation, x plus y equals to 2. Now, if you set this x, right, because you're integrating this x, x plus y equals to 2 is equivalent to say that x equals to 2 minus y. And so you want to stop at this blue line, and so you have 2 minus y at the top. Okay, if you put a 2 here, then you will go all the way to the boundary. And you don't want to do that, and therefore you want to stop at the blue line, which is 2 minus y. So you want to go here, go here, go here. That is your inner integration. Now, how about the outer integration? The outer integration is dy. The dy, of course, you go from 0 all the way to 2. Then just help you count all these yellow lines one by one. Then you go to 2, so that would be the outer integration. You put all these numbers up, and then the rest is just calculus. You can show that this is indeed 1/2. Okay, so let me draw a more beautiful diagram to make sure that you understand this idea. I believe that most of you have already learned it during your freshman or sophomore calculus. But if you have forgotten these ideas, it's not too hard to catch up. Let me just rephrase. This is the line that you're looking at. All right? This line represents x plus y equals to 2. We are looking at the lower triangle because the set is less than or equals to 2. That will give me the orange or the yellow area. And then I want to do the calculation for this area. So I want to integrate. I want to start with x first. So I have integration of x. And then the line has to go from this 0 all the way until I hit the red line. Okay, and therefore the maximum value I will be getting is 2 minus y. The 2 minus y comes from the fact that x plus y equals to 2, and so x equals to 2 minus y. That's the 2 minus y. And then I need to do the outer integration. The outer integration is integrating from 0 to 2 over the y's. Okay, so you may ask, is it possible that if I don't want to integrate dx first, I want to integrate dy first? Is it still doable? That's of course doable. You have this triangle, and then you want to integrate dy first, so you can do dy, and then you have the integration from 0 up to this point only. Do not go over that. And this point is x plus y equals to 2, and therefore y equals to 2 minus x. So you have 2 minus x. And then you have dx. The dx has to go from 0 all the way to 2. So this is 0 to 2. So this is another way of doing the integration. This is dy first and then dx. Here is dx first and then dy. They should give you the exact same result. And you can check this at home. Now here is another example. We have this PDF, and then the PDF is given by c times e to the power minus x, e minus y, and then the range is a little bit strange. It is y less than x. So we ask, can we find the constant c? So in this case, we can also draw a diagram and see what is the integration range. First of all, I know that to find this constant c, I need to integrate the entire PDF, and that has to equal to 1. And so I plot this number in, and so I will be able to write down my equation. The tricky thing here, of course, would be this integration limit. And what are they? Okay, so let's see this diagram here. I am looking at this PDF. It has some functional values, which doesn't really matter to me. The most important thing would be this range of numbers. This is y less than equals to x, and this is the diagram. Okay, y less than or equals to x. Okay, it is a triangle on the right hand side. Now you may wonder why is this? Okay, why not the other way around? Let's look at this equation, y less than x. We ask, let's look at y equals to x instead of worrying about the inequality sign. Y equals to x. Is it a straight line, a curve, or a parabola, or what is it? Of course, it has to be a straight line. What is the slope of the straight line? 1. And then what is the y-intercept of this line? 0. So what is the line? This is the line. Okay, this is the line of y equals to x. And then you ask, I have an inequality sign. Y is less than x. Should it be here or should it be here? Y is at the lower half. So this is actually quite easy. You pick a point. Okay, so pick a point. Let's say this point is 1 and 0. X is 1 and y is 0. Okay, so you put this in. So 0, you ask, if this is true. And there's clearly where y is 0, where x is 1, this is true. Okay, so this point is included, and therefore this area will be here. Now you may wonder what if I pick a point at 1 and 0? Okay, well, if you put a point is 0 and 1, okay, 0 and 1, then you have 1. You ask, is it true? Actually, this is not true, and so this point is not included. And therefore, if you do this calculation, you can see that your curve will be here, and then the integration area will be down here. And so you ask, what is the integration that I need to worry about? Well, you have two ways to integrate this triangle area. You're not integrating the entire square, you integrate just the triangle. So you can integrate. How about we integrate x first? Now, if you integrate x first, you want to go from this point all the way to infinity, okay, because this is unbounded. So you go all the way to infinity. Now the starting point is not from 0. The starting point is from this line. This line is y, because x equals to y. Okay, so this is the inner integration. The outer integration, you just go through all the possible lines. So that will be y going from -0 to infinity. If you don't want to integrate x first, you want to integrate y first. That's also pretty easy. So you go from what? You go from 0 all the way to this point, and this point is 0 all the way to this point. Now you're integrating dy. Y will hit to this point, that will be x, because this equation is y equals to x. And then you do dx. Dx will go from where? The dx will go from 0 all the way to infinity. Okay, and then after you've done this, you just put in your xy. Okay, you just plug that in, and then you can complete the rest by yourself. This is just calculus. Okay, so now you see that why do we have this equation here from 0 to infinity, 0 to x? This is because I'm using this integration with respect to y first and then x. All right, so I have y and then x. So that is the same if you want to try with the other approach. If you plug that number in, you will be able to show that this integration will give you a c over 2, and equating this to 1, you'll be able to get c equals to 2, which is the answer of this problem. So we have seen the joint PMF and then the joint PDF. The rest is just some variations of that idea. And here's one. It says it's the concept of marginal PDF or marginal PMF. The marginal PMF is defined as just the PX or PY. Marginal PDF is the FX and FY. So if you have a two-dimensional function, which is this is x, this is y. If you integrate over all the possible y's, then you'll be able to get down to one line of numbers. That will be your x. Okay. Vice versa, if you integrate this y, you integrate over all the x. Okay, so you integrate all the x in this way, then you'll be able to get to a PDF of the y. Okay, so that is just the integration. If you're integrating the y, you'll be able to get fx. If you integrate over the fx, the dx, you'll be able to get the y. So that's called the marginal PDF or PMF. And here's a very simple example. Let's say you have this PDF, joint PDF, which is a uniform distribution in this area, and then you ask, can you find me the marginal PDF of this joint PDF? Okay, so here is your x, this is your y, and then this is the orange area. Okay, so you ask, how can I find the fx? Okay, find fx of x. Now to find fx of x, you just need to integrate this vertically. So that will give you an area like this L shape. Okay, because you have 3 coming from these three yellow squares, and then you have 1 coming from here. So that will give you this fx. And how about find fy of y? Find fy of y, you integrate horizontally. That will give you a shape like this. Okay, and so if you look at this diagram here, I've drawn the fx and also the fy. These are just the marginal PDF of this joint distribution. Of course, you can write down the equation more carefully. So you have this fx is between these numbers, fy is between these numbers. Here is another example. Let's say I give you a joint Gaussian random variable. Of course, I haven't defined it yet, but let me just tell you the PDF. Okay, so the joint Gaussian random variable has this PDF. You have a sum of the two square terms. We want to find the marginal PDF of fx. Now, how you do that? You integrate this PDF, joint PDF, from -infinity to infinity for the other coordinate. So you put this in, and you do the integration. And then when you do this integration, you observe one very special thing, that this term that has everything to do with the x has nothing to do with the y at all, because it is in the form of a product in exponential. Okay, so you can pull these two terms up out, and then you can write it as a product of the two individual things. One, you don't have the integration because it has nothing to do with your integration. Okay, there's a dy, it has no y. The other term will be the integration from -infinity to 0 to plus infinity, and that is the integration over all the y's. But this is just 1. Why? Because this is just the PDF of the one variable Gaussian, and it integrates to 1. So we have this eliminated, and so we have this term remaining. Now you can see that this is a very special example where this is a Gaussian random variable, joint Gaussian, and then if you integrate one of them, you just recover the 1. Okay. Pictorially, what it means is that you have a Gaussian. This is your Gaussian distribution. If you integrate vertically, that will give you fx. If you integrate horizontally, that will give you fy. Both are one-dimensional Gaussians. So I want to also talk about this concept of independence. Okay, and this is a very simple generalization of what we have learned in some time ago when we talk about independent of two random events. If you have two random variables x and y and they're independent, then you can write the joint PMF as the product of two marginal PMFs. If you have a joint PDF, you can write it as the product of two marginal PDFs. Okay, so what is the extension? Well, the extension would be that if you have n random variables and then you have n state, you can just write them as the product of all these individual marginal PDFs, which is very, very useful. Why? Let me show you why. Here is a n-dimensional distribution. If you ever want to calculate an event, what do you need to do? Well, you need to integrate this high-dimensional function all at once. Okay? And integrating a high-dimensional function is just not fun. How about this? This is a product of individual marginal distributions. So at most, what you need to counter is to integrate one and then take the power to the n if everyone is integrating the same interval. Okay? And so writing this n-dimensional function into a product of one-dimensional functions, that can tremendously save you a lot of computation if you know that the random variables are independent. Okay, and therefore the independence is a very useful technique to simplify things. So going back to the previous example, we have this joint PDF given by this equation, and you can write them as a product of two individual marginal PDFs. Okay, and therefore you can say that x and y, they are independent because you are able to factorize them into two different marginal PDFs. Here's an example where you cannot factorize. For example, here you have this minus of x minus y squared. If you factor them out, you have this 2xy. Now you have this extra term which doesn't allow you to write very clean results that fxy equals to something of x times something of y. This term has something xy altogether, and you cannot eliminate them. And that's why if you have a joint PDF in this form, then I'm sorry, they are not independent. Okay, and this term would precisely define the correlation between the two variables. If you have n random variables and they all have the same distribution and they are independent, then we use this term to describe it. It's called the independent and identically distributed random variables. We call them IID. This term IID is extremely important, okay, because if you know that the random variables are independent, and if you know that they have the same distribution, you can just write this fx1 xn into fx1 x1, the entire thing to the power n. I don't even need to worry about the other state because it will be all the same, because all these random variables, they have the same value. Okay, especially now if you have n of them, they are taking the different values, then of course you need to take the product. But if they're all taking the same values, then this is just f of x1 calculated at that number to the power n. So that will simplify the calculation a lot, and you will be able to see examples later on. Okay, so why is this IID so important? If a set of random variables are IID, then the joint PDF can be written as a product of individual marginal PDFs. This is coming from the independence property. Okay, and integrating joint PDFs is not fun. Integrating a product of PDF is a lot easier, right? So that is a computational reason behind why we want to deal with IID random variables. And I promise you will be able to see a lot of IID examples later on in this course. So let me just quickly give you one example. If you have all these random variables, they are IID Gaussian with each of them you have this PDF. Okay, so they have the same PDF. Then the joint PDF of all these x1 through xn, you can write down this joint distribution. It will become a product of the individual marginal PDFs, and then you can multiply them together. That will give you this factor. This factor comes from here into the power n, and then you have this exponential, you have this whole. Okay, so if they are IID, it will be very easy to write this joint PDF into this product of terms. Now, finally, let me talk about joint CDF. Okay, joint CDF is used less often compared to the joint PDF and also the joint PMF, as well as the marginals. But we still want to know some of the basic definitions of joint CDF. If you have two random variables, the joint CDF of x and y is defined as this x is less than x and y less than y. That's just a very natural extension of CDF to two-dimensional cases. How do we calculate the CDF from the PDFs? If you are having a discrete random variable, you can just sum all the x prime to x and y prime to y, where x prime and y prime, they are the dummy variables. Similarly, for the integration, you can integrate dx prime and go all the way to x, dy prime, go all the way to y. Here are two examples of a joint CDF, and then x and y, they're independent uniform random variables, 0 and 1, and you want to find a joint CDF. And so because they are independent, and so we know that the CDF can be factorized into a product of CDFs, which is the same as the PDFs. And then we write down the individual PDF, which is 1 inside this interval. And then you integrate from 0 to x, from 0 to y, and you have this result of x, y. Same here, if you have two independent uniform, you have two independent Gaussian random variables, okay, with the mean mu and sigma square, variance sigma square, then the joint CDF can be written as the product of the individual CDFs. Okay, and each of them will just take the form of the standard Gaussian evaluated at x minus mu divided by sigma and y minus mu divided by sigma. So this is the joint CDF of a pair of Gaussian random variables. There is a very simple property of a joint CDF, which is about the marginal CDF. If you plug in one of the coordinates to infinity, you'll be able to get the marginal CDF of the other. Okay, so for example, if you put y equals to infinity, then you'll be able to get fx. If you put x equals to infinity, then you'll be able to get fy. That's just coming from the definition, because if you look at the definition of this CDF, if you put y equals to infinity, let's say here, then you're integrating this, you're summing or integrating this 2D PDF or PMF for all the y's, and you know that by integrating over all the y's, that will just give you 1, and so you will knock out all the y's, and then you will be able to get x. So that's why when you plug in y equals to infinity, you'll get fx. You plug in x equals to infinity, you'll be able to get fy. So the last result is about the derivative. So if you start with a joint CDF, you take the derivative with respect to x and y, you'll be able to get the PDF of x and y. Okay. Now the order of derivative doesn't matter. You can dx first or dy first. That does not matter. So I hope this lecture we have explained some of the extremely basic ideas of joint distributions. In particular, we learned the joint PMF, the joint PDF, and the CDF. They are just high-dimensional extensions of the PDF, PMF we have learned in the one-variable case. The difficulty, I hope you can see, is that when you try to do the integration, the 1D integration will become the 2D integration. And therefore, you need to worry about the range, and you need to look at the shape under which your integration is taking on. Sometimes you need to integrate a triangle, so you need to worry about whether it's upper triangle or lower triangle. You need to do this kind of calculation. But beside that, everything should be pretty straightforward. The other thing that I want you to remember in this chapter is the notion of independence. If you have a set of random variables and they're independent, then you can write your PDF, the joint PDF, into a product of marginal PDFs. This is an extremely important result because that can help you simplify a lot of calculations. There is one special term called ID, which we will see them again and again in our course. This idea means that they're not just independent. These random variables, they also have the exact same distribution. And by exact same distribution, I mean that they have the same mean, same variance, and same PDFs. And so by knowing one, you know everyone. So this independence in ID structure will help us do a lot of analysis for complicated problems. And so I hope that you can spend some time trying to understand the meaning of independence here. So this is the end of this lecture. I hope you have found this lecture slightly boring, but I hope you have found this to be still pretty useful, because without knowing these basic ideas, it would be very hard to generalize our concepts to practical problems. And by practical problems, I really mean that problems that involves high-dimensional space. You have vectors, you have matrices, you have many random variables working together. And so knowing some basic ideas on the joint distribution is really the first step to go into practical problems. I hope you have learned something here. If you have any question, please feel free to post your question up on our Piazza forum or send me an email. Please also check out the ebook. There are lots of details in the ebook, which I haven't been able to cover in this lecture. So take a look and try our homework problems. So thank you very much. I hope to see you next time.